Welcome to video number 5 of a series of short lectures entitled The End of the Calories In, Calories Out Theory. My name is Francisco Arencibia-Albite. I am an associate professor of Human Physiology at the Universidad del Sagrado Corazón in San Juan, Puerto Rico. The aim of this lecture is to solve the system of linear equations that emerges from the intake-net-oxidation diagram. The material here presented is not required to understand the final lecture. Therefore, those in the audience not interested in these mathematical aspects can skip the presentation and proceed to the final lecture. In lecture 3, we use the following diagram to formulate the next system of linear equations, where the net oxidation terms are unknown quantities. It was claimed that the solution is given by the following set of equations. In this lecture, I will explain how to arrive to such solution in step-by-step fashion. The first step is to set the matrix that corresponds to the system as shown. Next, I want to perform row operations in order to generate zeros below the one in the first column of the matrix. First, I subtract row 1 times the fat energy density from row 2, and the result becomes the new row 2 shown in red. Second, I subtract row 1 times Kf from row 3, and the result becomes the new row 3 shown in blue. Thus, the new matrix becomes. I now want to place a 0 in the position labeled with the red box. This can be done by performing the following row operation, where I take row 3 times the difference between the energy densities of carbohydrate and fat, and from this product I subtract the product of row 2 times Kc minus Kf, resulting in the new row 3. In this new row, A is equal to the following expression, that can also be written in the following form, and B is equal to the next equation. The matrix has now zeros below the main diagonal, and for convenience, I want to multiply the third row by the reciprocal of A, which gives the following matrix. Here, B over A equals the next expression. At this point in the solution process, I want to replace the matrix notation by the system notation, which produces the following system that can be solved by the procedure known as back substitution. But to make such process less cumbersome, I want to first simplify the expression for the net protein oxidation. To start the simplification, recall the BO2 asterisk formula. Then rearrange the expression as follows. Note that the term in red also appears in the fraction for the net protein oxidation. Thus, after substitution, we get. Next, observe that the expression within the green box can be rewritten as the expression in blue. Substitution of the latter expression into the numerator of the net protein oxidation gives. Expanding the expression yields, or the terms in green cancel. Therefore, the numerator of the net protein oxidation simplifies to the following expression. The expression in the box can be rewritten as. Note that the expression inside the curly brackets can also be written as the purple expression. Substitution of the latter into the curly brackets produces. This result is the simplified version of the numerator in the net protein oxidation fraction, and thus this fraction can be decomposed as follows, which leads to the final simplified version of the net protein oxidation. To be clear, what I have done so far is to simplify the bottom equation of the shown system into the purple equation. Thus the system becomes. Substitution of the bottom equation into the second equation produces. Expanding the second term of the left-hand side produces. Here, the terms in orange and green cancel out, obtaining. Solving for the net carbohydrate oxidation gives. To finish the solution, we substitute the purple and orange equations into the first equation, which produces the following expression. The terms in the green boxes cancel, and so grouping like terms produces. Finally, solving for the net fat oxidation gives. In conclusion, I have shown that the following system of linear equations that emerges from the intake-net-oxidation diagram has a unique solution, given by the next set of explicit formulas. I hope that the solution deduction has been useful. Thanks for watching, and I see you in the final lecture.